pressure that actually does the work, and you lose some of that. It's like, think of the X-rays as an expanding gas, so it loses energy as it expands into this. So I've got to pick something out there to contain this material, and there are several ways to do that. Those of you that are into hot fusion know that you get all kinds of instabilities. I did this after I got a lot of questions yesterday. The instabilities of these things, if you take a tube with water in it, you can move water up and the gas will come out fairly easy. Whether you're moving it fast or slow, it doesn't matter, in a big tube or a little tube. If you have tubes and you try to move the water with air pressure, a large tube, you'll get bubbling and that sort of stuff. These are Riley-Taylor type instabilities. Or if you have a thin enough tube, you can actually blow through there and blow it out, but you have a chaotic system. Those instabilities are what's affecting a lot of these plasma type things. You can do it with your magnetic field or X-ray pressure, but basically that's zero density material pushing on a high density material. So you get all these differential equations that go chaotic. So you have to pick something that has a higher density than the thing you're pushing. If you go through the chart, if you're starting with palladium, you're left with these materials that have higher density than the palladium's pushing there, so you don't have instability. Keep in mind that titanium is less. I'll come back to that in a minute. So you have to have lower, the thing inside has to be lower density of the things outside. You also want things that have a reasonably good melting point so that it melts off in a blaze. Going back to this picture here, your ablating material, as the electricity goes through it, it will heat up and this will come out and there's a reaction force pushing things in. So you want some of it to go off, but not so much that it just goes off before the inside kicks off. So you go through the various materials, and the things in red are those that have the right kind of melting points for what we need to do if you're using palladium. You also need, those are the density. The electrical conductivities, you want to have them a little better than your palladium. That doesn't want to focus. Oh, careful. Okay, that's why. So these materials are suitable. You want things that so that when you load your wire, most electricity goes on the outside. When I'm taking the wires, I load them up, the deuterium goes in, the resistance almost doubles, 80-90%. I'm probably around 0.6 PD ratio in the wire. Then you put the gold plating on there, and it lowers the resistance back down to where it was before. But you run electricity through there. They're very short pulses in microseconds, which goes on the outside, blows off some of the gold. As the resistance to gold starts decreasing because of the loss, more goes through the palladium. So you want the right kind of resistance. And all those things are interconnected. In the case of palladium, after you put those factors together, you're basically left with a tamper. Gold is about the only thing you can use. It has more density than it, right kind of electrical things. 2 minutes. Oh boy, I haven't even got to the result. With titanium, you can do a little better than that. I won't get into the neutron reflectors. Okay. The other thing that the tamper has to have is it's going to have a high Z number, because when I get up to 35 kilo electron volts in the deuterium in the wire, you get a lot of X-rays and it will rip apart most things. So you've got to have something with a high Z number, gold or uranium or something like that. So you got to have Z's above 51 to have at least one electron left on there, so the X-rays from the inside do not emit out but reflect in, preferably above 71 in order to have 2 electrons in there, even better, more opaque. Tell you the chemicals. I've got the chemical materials. What I do is this is the design requirements. I've got to have all those factors I mentioned. I am at 8,000 feet, so I have my room at a constant temperature, constant relative humidity and pressure. I only pick clear days. That's low pressure where I am. I control the temperature of the room, my capacitor bank, that sort of thing within fractions of degree. And I follow a detailed protocol of waiting for the capacitor to get the right temperatures and all that, so I have equal energy in storage. I then take data, and if you look at it, they're fairly close together, and in these charts, I'm putting in about 1.2, 1.3 KeV. I get out about 10 joules more, and one more picture. That's when you plot the two. The red one is with the deuterium. This is with hydrogen. I'm still within a sigma, but it's obvious that something moved. So I'm getting more power out on these deuterated wires, this hydrogen wires, so I'm producing about 10 joules of fusion power. Yes, any questions?
Okay. Oh, what about the loss?
Is that a question? Oh, I thought that was...
No, okay.
Okay, for those hot fusion people, I am basically got a new cow, and the Lawson criteria for hot fusion criteria for D is 10 to the 16th seconds per cubic centimeter. I'm at about 10 to the 12 EV per electric pulse in a small containment volume, about 1/1,000,000th of a cubic centimeter. I have equal atoms of deuterium and palladium.
So we aren't in question.
Oh, okay.
There is a question.
Okay. So I'm basically at or equal to the Lawson criteria right now. Yes?
So you measure your input energy with product of I times V integrated physically?
I do it. I have a capacitor bank. I charge it up to 4,200 volts. I let it come down to 4,000 and I pulse it. I keep the capacitor bank at constant temperature, so it's always had the same storage. So my energy, the same energy is done because I've got the same 1/2 EV squared in my capacitor bank. It's still in Does that mean I'm over?
No, I still have a few seconds.
I'm happy to show you out.
Basically, you built a small hydrogen bomb. So
Yeah, basically.
Have you tried to load that palladium wire with basically the same constituents that are used in a hydrogen bomb, like lithium or anything?
I can't get the lithium inside the palladium. I can the deuterium. I should be hotter if I ever got tritium deuterium into the wire, but I don't do tritium. This is just backyard stuff, so.
Okay.
I measure the heat by putting it under water so the temperature rise of the volume. And now I'm doing it by exploding a gas and getting the time of flight.
Welcome, Larry. This is going to go a little over, so.
Time of flight of a proton.
All right, this is from Dr. Eugene Mallove, Dr. Eugene Mallove was the chief science writer at MIT at the beginning of the controversy, and because of really serious problems and trying to convince people that he was real, he resigned and started his own magazine.
Here in the offices of the Nuclear Energy Magazine, New Energy Research Foundation, and we're honored to be able to speak remotely, transparently, for the APS meeting, and this is a matter of my thought. Got it? From an enlarging perspective,
Yeah, I got it.
whole fusion and new
My
energy.
acoustic's got it. Got it.
Something to expand the ideas of what initially we thought was a restricted field, but in fact turned out to be a larger field. We're a non-profit organization here in New Hampshire, and we've been publishing magazines, 50 issues now of nuclear energy since 1995. So that's been the whole fusion war since 1989 when it began. The war began, but the present war when it began. We do have some websites of interest that we want to draw your attention to. 3 of those important for the whole fusion field are magazine reports, then LENR-canada.org, and also wildlife power.com. can't really understand new hydrogen energy physics if you don't consult regularly those sites. Okay? There are some other important sites, however, that considerably expand the range of our interests. There's a magazine that deals with this, mainly vacuum energy and other forms of new energy. Deuterated.com is one of the sites you should read. And another is Energy Sciences, that company out in the UK. Dr. Howard Aston, maintains that site. Indeed, our interests at Nuclear Energy Magazine are threefold. We have interest in new hydrogen energy physics, vacuum energy, and advanced thermodynamics that deals with extensions to the second law of thermodynamics. In fact, we recently had an issue on the topic, the death of entropy. Yes, it is dead. That's sort of our layer, published about this paper from the people at the University of San Diego, published in Foundations of Physics, October of 2002. Sheehan et al., solid state Maxwell's union. Indeed, the second law seems to be going the way of the other. This is the full paper, but you can certainly get a copy of it yourself, the PDF form, or whatever else. How did the cold fusion field get so maligned, such as all other new energy fields? Anytime new energy comes up, there's always a maligning. Well, certainly in the case of cold fusion, which is the gentleman lately of cold fusion of new energy, much earlier than that, doing the other devices that predate cold fusion by many, many decades. But this Department of Energy report, this is what the paper is written on, was written in 1989 November. It started the whole thing going in the wrong direction. We tried to correct it, and nothing seems to have corrected it, at least in the public perception. My book, from Ice, in Charles Beauvet's book, two MIT graduates who've written cold fusion books, on the concept. And mine was the earliest one, 91. Beauvet's was year 2000. Both played a role in the start of cold fusion. The most important document that I've written in addition to the book was this 10th anniversary review of the contributors, of course, but my 55-page report on the travesty that happened at MIT, the flaw, the press installation, and so forth, is all in here, and we're now going to post that 55-page report on the World Wide Web, so everyone can see it. Indeed, it was an example of what can only be described as heavy water. The original cold fusion matter cycles of the water. We have the three big negatives, supposedly. MIT, Caltech, and RLR in England, all three have problems. MIT is the worst because it involved in lack of ethics. Cited the fraud for that. Point of fact. You can read your report and find out why it is fraud, because that's exactly what it is. Moving and shifting from a positive result to make it look negative. And this is my overall statement to the APS. I think you need to see some opinions about the ethics and the accountability that has been lacking in this field that is against cold fusion. The latest issue of our magazine, Peter Harrison on the cover, has the central issue that began with the problem with cold fusion and the problems that happened at MIT. Okay, and we now hear, by the way, that MIT President Charles Vest has been nicknamed by President Bush to head the new task force on science for all future energy science in the Department of Energy. Isn't that wrong? Because he's the man who, more than anything else, keeps the whole matter of investigating the law. On Ether Energy, by the way, there is a DVD available, which was put together by the Cravens, myself and Dr. Aston, and this deals with the matter of vacuum energy. You can order that on Ether. There are actual working devices today that demonstrate new forms of energy that may in fact be connected to cold fusion, but we have to see the DVD to understand that. I must tell you that there are other forms of energy that we featured in infinite energy. The spark work, arcs underwater by Peter Neil Renault, as well as his form work that are all anomalous and really unique. There are other devices, rotating devices that cavitate in the water, and those appear to produce excess energy as well. The hydrosonic pump, the kinetic furnace, and so forth and so on. I recently heard from Ralph Hope, and by the way, excess heat is back from this rotary device that spins and cavitates under the water. Okay? That are all fusion. But the real payoff may indeed be vacuum energy. And as far as vacuum energy goes, in the Beerman's work, you can read about the Cravens in issue 70 and 9 of Infinite Energy. He has a United States patent on the pulse abnormal low discharge reactor. Go to their website, Enlarging.com, and you'll find precisely how to build such a reactor, and it's already a 10 to 1 power ratio, far beyond anything in the cold fusion field as far as a repeatable device that absolutely, as far as I'm concerned, verified and validated. Maybe not by a large number of people, but by industrial groups that have come to see it. And with that, I'd like to just put on a few little video tidbits. I do have to apologize to you. I was prepared, I thought, to play some of the DVD into a recorded format on the VHS tape that I'm sending by trying to do it DVD video. We just have to get it set. Or do it with me at some time to visit the energy research, the energy foundation. Apologize. But I'll show you a few gadgets nonetheless. This is a modified version of Roger Streaming's device that we made here at the Energy Research Labs and tested it extensively in Cedar Valley, California, finding some evidence of excess heat, but not as much as Roger had originally thought was device that purchased from him for a pretty penny. We modified it, made it smaller so that we could test it.
That's the cavitation device.
Cedar Valley, California, this is what it looks like. By the way, we have many other museum pieces here. We have a lens case cell. This lab here, the Energy Research Lab, is in fact the first lab to confirm independently that he did have an excess temperature effect. There was like McCooley and others found helium their product, was there, is there, repeatably, apparently, and correlated with excess heat. But it looks like a crude device. And it does use what looks like crude material, namely carbonized coconut shells with palladium coatings on it, but it does work. In the area of vacuum energy, by the way, these are harder cages.
He's going on a little bit. Unless you want to see that. You want to see, well, I mean, sort of. If it's all right, I'll give it.
Go on.
Go on.
No,
He's going over a little bit.
no, program up the speakers.
No, we're almost at the end.
You'll come out of your time.
We got to take the tour, that's going to
And around a little bit, here's a Radlin non-working cold fusion cell trial configuration. And we bought two of these. Chris Tinsley tested one, did not work. The understanding is Dennis Cravens tested another, and the third one. So what do you have? Not the way that I don't see so much, but it's kind of amusing that the hot fusion people back in 1989 actually purchased these mugs, cold fusion confusion, and this is the nature of the cell, with the wire, copper sulfate on the bottom. This is a joke about cold fusion. It should have been analyzing a catalytic, but instead they were selling these, purchasing these little charge fees at the time. I don't know whether we have much time, but even if we don't, I want to tell you that there is a very intimate connection between the ether physics, which is
Gene has preceded the problems that occurred with the APS. Things are sort of getting screwed up. Okay, Dennis, you left this. All right, so anyhow, moving on now. Well, we have a talk. Professor Miley from the University of Illinois is going to give a talk entitled Deuterium Loading in Palladium Thin Films Prepared by a New Co-Deposition Technique. Ni Luo is the first author. Unfortunately, he couldn't come, but Dr. Miley Professor Miley is going to present it in his place.
That's a hard act to follow, but I'm going to pick up things. Since ads were given, I'm going to give a little ad for work we've reported in previous sessions here, and steal a couple minutes to talk about our work on transport through various films, because I think it's very important. And what we've been trying to do is understand this exceedingly important experiment, which was reported by Muir et al. Mitsubishi Corporation of Japan, where they put this atomic layer of either cesium or strontium on top of a thin films, and by gas pressure, diffusion through the film, atmospheric pressure, deuterium simply diffusing through, observed a nuclear transmutation of the atomic layer and top. This happens to be the cesium, starting at around 10 to the 15th atoms per cubic centimeter, per square centimeter, over 100 hours, decreasing order of magnitude, and praseodymium coming in at roughly the same rate. So that the observation is that they created reactions in two separate types of experiments: cesium, praseodymium, strontium, Mallove, exceedingly striking, and this represents a mass difference of 8, Z difference of 4. So it seems to involve 4 deuteriums reacting, and our theoretical studies have concentrated on using density functional methods to study the electronic structure and accumulation around deuterium and hydrogen loaded into palladium labs. And I'll show in a minute how that relates back to the Muir experiment. But for example, at octahedral sites, we see that there's a slight accumulation of electrons around the hydrogen, which is located at this point, negative being electron accumulation. And we've also looked at other sites, principally what we call hopping sites near the edges, where the deuterium has to pass as it hops into the medium in the diffusion process. And so now what we've done is put in to the surface layer of the palladium cesium, and cesium is a big atom, as you know, and so you see it really fills things up. And now when the hydrogen or deuterium hops through these hopping sites, in between there, tremendous electron density is accumulated to get a orbital mixing, what we call virtual neutron formation, essentially, which allows the collapse of the 4 hydrogens that are around the cesium to collapse into a tunnel and react. So that's in paper V35 earlier. So let me jump to this loading paper. As people in the area know that the Navy spar wire people use this co-deposition
technique previously with quite market success. So what we're doing is, by success, I'm saying to be able to get repeatable excess generation. So what we're saying is that, well, let me jump back. Why do this type of deposition where you're laying down hydrogen or deuterium and palladium simultaneously? Part of the reason is that you reduce the stresses, stress related effects, because you build in the hydrogen as you lay down rather than put it in to cause expansion and stresses. And this also seems to ultimately lead to this repeatability. Problems with the original methods of doing this seem to be a limited hydrogen flow rate, which we think is necessary as well as a high loading, and also limitations in the duration that the effect could be maintained. So we've looked at this alternate process for doing it, which would attempt to get around that, and have used a thin film cathode as a substrate essentially to increase the flow rate, and have a consumable anode that allows you to continuously run plants in the palladium. And so the setup is like so. The main anode is here, cathode is thin film, the sputtered on to start with, but now the associate palladium anode, which since now it has separate power supplies, so you can control the relative voltage across builds up the palladium by plating out here onto the surface of the thin film. And the typical conditions for that are this V1, which is between the auxiliary anode and the cathode, 3 to 4 volts, somewhat lower back to the main anode to the auxiliary. We're using lithium sulfate with added HCl for the transporter. And so with that, here's a picture of our thin film starting anode, which has an error here to increase current densities. And we get quite nice calorimetry, maybe order of 70% excess. This is a quote typical run where if you look at the first part, we didn't change things much, and when we could maintain maybe a 7% excess, so we were changing a lot of things, still excess varying. So the conclusion is that we've done this now enough to argue that this particular process does give good repeatability, and the generation lasts over a number of weeks. Actually, it's only limited, we think, by the lifetime of the consumable anode, but we can put a new anode in, so it has a long lifetime. Thank you. Any questions? Yes.
George, I didn't see any V2 involved. Was you use HCl? Was it water?
Yeah, we're using light water.
This is light water.
Normal.
Normal water.
Normal water. Yeah. It always has a small component. Yeah, but in our studies, we've added some, over time, we've added D2O in. That hasn't changed the results.
Could be one part that could be that small side.
I don't
D is doing.
I don't know.
I don't know either.
Well, where we measure transportation, it's very hard to believe.
So there are any other questions? Yes.
Do the slide with the transformation quantities again?
Can you stand up?
With the transformation quantities again? Can I see that slide again? How much was actually transformed into this other element?
Transmutation.
Transmutation.
I went around, it's like,
Unanswered, yes. That's available on the web, actually, the paper.
Yeah, well, he started about 10 to the 15 atoms and went down to virtually 10 to the 14, so it's per square centimeter, so it's very significant.
It's a spectacularly well instrumented.
And used XPS in situ, so, and with deuterium gas, you can't really find a purity source that's going to give these products. So, I think that is a seminal experiment that has to be understood in this field.
Any other question?
So
Go ahead.
how do you extract the heat? So how is the hydrogen flow? How effective is it? Because, I don't know, it seems to me you have to push it or something. And you have to include that as well. To be able to operate, to be economically.
I'm not sure I understood, but we have these previous papers, we're trying to post some on the site, but we've done a lot of study now of hydrogen or deuterium flow through these lattices. I would refer you to that.
The technique, which one are you referring to? You're referring to the second thing you're talking about, the co-deposition? Yeah, well, our report, which he referred to, has actually been a decade-long work. What they do is they have, what is it, palladium, they have palladium chloride and, they do a co-deposition of two compounds onto a substrate. And the heat occurs after the co-deposition has been, in other words, it's all electrolytic, and you put the stuff there. Did you see any X-rays? Did you look for X-rays?
We haven't done that yet. We're going to look for X-rays, anything else. 16 may be off the part.
Well, these people saw X-rays. The people in question are Stanislav Spock and Pamela Mosher. Okay, you're welcome. See, I'm the last talk. I'm going to call upon my uncle, Chubb, to be the keeper of the time.
Be mean, Talbot.
Yeah. Your turn, Talbot.
You can handle it. The title of my talk is Importance of Broken Gauge Symmetry in Addressing Three Key Unanswered Questions Posed by Low Energy Nuclear Reactions. Now, the purposes of this talk, because of the contentious nature of the field, I'm doing this for Research Systems Incorporated. And this is actually where the work has been done. It's been done on my own time. Even though in other contexts I've been in the role as well. How is it possible that the three key unanswered questions occur in low energy nuclear reactions? How is it possible to couple nuclear and atomic processes, the very disparate length scales? How can that occur? Are bulk processes involved? And this alludes to some of the stuff that my comments about what Ed Stone was saying. Can the effects of bulk solids on surfaces make this occur in a non-local way? Now, it's not inconsistent with the kinds of things that Peter Hagelstein refers to. It's simply at a very different temperature. In fact, much of what Peter and I, we started to understand each other better. And I think that, we're sort of coming towards a common framework. I'm going to allude to outside the box, and I'll say what we might, in this one view graph, I'll say that's what we might suspect to be true. Unconventional physics. Later, I'm really going to talk about, up here, mostly things that we think about either within the context of what we really mean we think might be true, but we're not quite sure about. And so this isn't really fringe physics in what follows. But in the context of this view graph, I speak of it that way. Then inside the box, I've drawn a box in a number of view graphs I'm going to talk about. What we know is true, that is based on conventional physics. Now, in conventional fusion, we have a neutron and a proton, and you have a proton-neutron pair coming in, forming an excited state of the four nucleon composite going off. And here we have helium-3 plus a neutron, and tritium plus a proton. This reaction, which is the one that Peter was pointing to, and the only way to treat this is the kind of way that he was pointing to. This reaction involves a critical coupling to the electromagnetic field. The deuterons actually have to be both symmetric, like a molecule, which Peter alluded to here. And actually, it's been very well studied from the dissociation of helium-4 by a gamma ray into two deuterons. This one rarely occurs, and it actually is because this thing must be like a molecule. They missed that point initially. So I've drawn it on the boundary here because EM, electromagnetism, is critical, and it's not been treated correctly, and was not treated correctly in the early discussions. So, what we expect might be true, but really, classically, we deal with we would think we could deal with the B field. The B field, though, has this problem. The problem is that the curl of J, this is the current, this is just Maxwell's equation. Actually, there's a plus 1 over C d E dt. I've been going that for the purposes of this video. No, actually, that's included. The plus 1 over C, that comes over there. This is actually, this is the classical wave equation. But it's actually poorly defined quantum mechanically because to measure it, you can't measure this quantity with a single measurement. So, as a result of that, we have to deal with vector potentials defined in this manner. And this is what gives us the notion that lights are photons and each photon travels at the speed of light c. But the problem, and the way we do this is we write B as the curl of A. This is the quantity we deal with. This defines photons. And we also have E is equal to minus 1 over C d A dt. Then we have this nice equation we can work with, and we can actually measure J. The point is that J involves the momentum, and there's an uncertainty relationship implicit in that. And when you start to do this, you have to perform more than one measurement, and that's important. So we believe this to be true, but there are funny things about this equation, and I'm going to get back to that. They come about when we do what we call a local gauge transformation. The notion is we start out with a wave function, and we multiply it by phase that depends upon position. Now, when we do this to the commutator, this is actually fundamental quantum electrodynamics. This is where quantum electrodynamics begins, talking about the nature of the electromagnetic field. Fermi wrote down this relationship, and he said, well, we run into a problem if del dot E is equal to 0, this thing has to vanish, and that introduces, in quotes, the problem that you don't have transverse photons. So, but that actually, suppose you do a gauge transformation on this, and you ask what you get. Well, you start out with an initial field, and there's commutation, and you can do what Fermi had, but you get this additional term. Now, if in a real situation, if you have a coherent behavior where there's a phase, it will not commute, by definition, with the density. That's a fundamental quantum mechanical relationship, so that you can't, so in that kind of situation, that's called broken gauge symmetry. You've introduced the gauge, and that's how that happens. Now, there are real concrete things that happen as a result of this. In particular, the basic statement is the vector potential A, when in a situation where you have a trapped configuration of light impulse, which occurs when you don't have del dot dAdt, that is, del dot E is never 0 in a particular body, so that you get photons emitted and absorbed. This can give rise, these are effects that we know, this is the basis of solid-state physics. Other people have called them by different names, and they refer to them in the jargon of non-Hertzian photons. We don't think of them as photons. We think of them as, for example, as lattice recoil, where the whole solid can move. And it's just a rigid motion. And so, if one views them as photons, they appear to have arbitrary speed, but that's stupid. That's not what happens. We're talking about wave-like behavior. And the point is, A and E can never be measured separately in that kind of context. And so, the normal free space attitude is you can do this, but that's not true in solids. An illustrative point involves, when you look at this situation, you're trapping photons. Here's I'll put forward the following thought experiment. We have an observer. He's sitting in a solid that's at rest. Now it goes into motion. All right, I've got to move here. If he's at rest, the wave function is 1. If not, there's a plane wave that multiplies it. Quantum mechanics doesn't say if the solid observer is in motion. That's the same thing I was saying. This is called the gauge symmetry. Energy is lower, though, by reducing the symmetry. The reason is the lowest state has to have the least overlap with other outside perturbations. It's important when the total momentum of the solid is relatively low. Now, what one can do is to put in some numbers and think about it in a rigorous fashion. The overall point is, this factor, e to the I k dot RCM, if the solid moves without interaction, that's its wave function. If you break up RCM into individual pieces, each of those, in the parlance of high energy physics, can be called a Goldstone boson. They're instantaneous because of these longitudinal photons. So if you have P equal H bar K, and that's the relationship. The A changes by a particular amount associated with the momentum of the entire solid. So that you get a ratio, you get a fractional distribution of momentum to all the individual particles. It should be an H bar there. You can calculate a reaction rate expression that is based upon the kinds of expressions that Peter Hazelstein was writing down. There's a particular formalism called multiple scattering theory where you can relate these terms associated with a matrix element to actually the fluxes of current coming in and out of locations where boundaries occur. And you can, in the limit in which, now the point is that this J can have momentum where reactions occur, but there can be regions of space where you have collisions, where that occurs, regions of space where that doesn't occur, where the solid moves as a whole. So if you picture little nuclei in particular locations where they're interacting, the whole thing can move and absorb momentum so that in the bulk region, there's no real change. Okay. And so you arrive at a particular kind of picture. You don't know. The important point is, within this context, you do not need periodic order. Paul seems to implicitly say that you do, but it's not actually required. There's a formalism that many-body theory does work. And finally, go to my conclusion. Emissions have occurred in pictures about the role of electromagnetism in low-energy nuclear reactions. Spontaneously broken gauge symmetry can explain how coherent coupling between nuclear and electromagnetic interactions can occur without high-energy particles. I didn't emphasize that point, but because if the momentum is shared by many particles, there's no large momentum in any individual location. These same forms of coupling also explain how LENRs can occur in which effects that are in the interior bulk regions of the solid can become coupled to surface regions where the gauge symmetry is required. The important point is it's temperature dependent. At higher temperatures you will get a lot of the kinds of things that Peter said. It's also dependent upon conventional many-body physics, and a formalism does exist for describing it. Questions, players? Yeah?
You mentioned higher temperatures. Are they temperatures we normally see in a small laboratory, or are these extremely high?
It depends upon the crystal size, and it depends upon a number of factors, and the phonon spectrum. Whether you're, good crystals at low temperature, can be very helpful, or I say moderately sized crystals at say a tenth of a micron kind of size. As you get up,
do we see what you're talking about at 50 C or something, or?
Oh, absolutely.
Okay.
Room temperature. When I say low temperatures, but if you have really big crystals, you can run into real problems. Now, I think an important point that I didn't emphasize is, I think there's a real need to have detailed calculations here. One can actually do detailed computations. I've shown a depiction here. This is actually a generalization of band theory. You can divide up the entire momentum operator. I didn't really talk about that, but you can divide up the entire momentum operator and in situations where you have a constant change of the vector potential. A constant change in the vector potential would move the solid. You're essentially shifting the zero of the momentum. And the point is that in the interiors of nuclear regions, you can have momentum, finite momentum. The momentum can be imparted coherently just through the notion of that Goldstone boson. Now, the point is that the Goldstone boson, these are arbitrary plane waves, and at the boundaries of the solid, that's where the interactions will occur. The arbitrary plane waves, quantum mechanics doesn't distinguish whether you're in motion or at rest. Yes.
Yes. One more question.
This issue was...
No, you're not timing. 2 minutes.
This issue was spontaneous broken gauge symmetry. I mean, there is a theorem called Elliott-Suhr's theorem that states that you cannot spontaneously break a gauge symmetry.
Oh no, that's not true.
That's true.
In what system?
If you had any gauge theory...
No. That's at high energy. This is not... No. Back off. The notion of... You're thinking of a different form of spontaneously broken gauge symmetry. The notion of spontaneously broken gauge symmetry is at the heart of condensed matter physics. It's the basis of superconductivity. And band theory actually actually is a form of broken gauge symmetry. The notion of breaking gauge symmetry is the statement that, in the language of this kind of thing, it's a statement that you can't arbitrarily define the zero of momentum. You can allow for the thing to rigidly move. Now, the actual answer to the way the things work is you include all possible momenta overlap with what happens at the boundaries. A key thing is, within this region you have charge neutrality. There are regions where you have charge neutrality and so forth. Now, the fact is, charge neutrality is the key aspect to this. That's what really breaks the gauge symmetry. In a global sense, what you'd say is correct. Yeah. I mean, yeah. Give it the
This to the mass power effect?
Yes. Yes, that's exactly. I mean, that's what it is. The last recall that I cited here, the Mossbar effect is essentially picking out a single wave vector in this little pictorial that I said. The point is, you can't tell if the solid is in motion or at rest. You know, when you move, you're not doing anything to it. That's the point. And you see it as being neutral. So the photons in here are trapped in quotes. But you're moving. Now, what actually happens? Well, and you say, well, are you moving or is the solid? Well, if you say the solid is moving, it goes through this transformation. Those are the Goldstone bosons. Now, the point is, you actually know that within some tolerance, the solid actually is at rest. There are uncertainties within this, K, and they can be rather small on an individual basis, on the total thing, but they can add up, and that's actually the origin of how longitudinal photons come into the process. Okay, now.
So how does it give you an idea that we cannot be able to have a chunk of solid to be able to give you a...
This limit only applies to both.
Got, you need to discuss this offline.
Yeah, we got Victoria's talk. Now, mine was the last talk of the session, so the session is officially over, but for people who are interested, there was, I mentioned at the very beginning, there was a poster that I gave on Wednesday that gets into the combined Italian SRI effort that describes actual detailed work on transmutation work that's been carried out over the years. And I can present some of that if people are interested, or we can just break. People, I would suggest that, well, I'll start it, and if you're bored, just walk out. There's some history here that's interesting. The Italians and the U.S. developed a particular project of work. Break that.
This is Peter Heckel.
The SRI?
The
SRI group, in particular, has done seminal work involving the helium-4 measurements, and as part of their efforts, they have transferred experiments that were conducted in Japan and brought them to the United States. One of the people who was really very important in this
Mr. Melvin H. Miles and
was
Bush.
a man named Francesco Scaramucci, and there were people who worked with him, and Mike McCoubry, another one who's very important,
Dr.
is
Scott
Mike
Chubb,
McCoubry.
NRL.
And here's the, so I presented this in a much longer form on Wednesday, and some of the material is, I'm certainly not the world's expert on some of the things that I did, but I can just give you a flavor of what they did. Vittorio Violante, I don't remember, these people are all associated with ENEA in Italy. That's the equivalent of, what's the other?
Miley.
You remember what that's the equivalent of?
Chicago.
It's their national nuclear agency, isn't it? I believe, well. And SRI International. Now, a research effort developed within the framework of a cooperation between ENEA and SRI was mainly oriented to perform electrochemical experiments to investigate the emission of X-rays during electrochemical hydrogen loading of thin metallic films of PD and nickel, and to monitor the inventory of marker elements in the electrochemical cells. So they put particular things in, and they looked carefully at how they changed. They also did a replication of the double structure cathode experiments for helium-3, for looking for helium-3. This was work that was errata. This is the errata experiment that you've been done. Now, I'm going to give you the conclusions in case you want to walk out. And I'll get back. The control of contaminants ensured a satisfactory signal-to-noise ratio in the measurements. X-rays have been detected in the low energy range, 2 to 10 keV, with enough reproducibility in the case of PD and nickel-based thin film cathodes. These results seem to be in agreement with a theoretical approach suggesting energetic particles could be created by coherent oscillations of the Fermi-level electron. This was due to an earlier theorist, Giuliano Preparato. The material balance led to studying the isotopic composition for some of the marker elements. Isotopic shifts had been observed for silver, zinc, with an enhancement of the 109 to silver, 107 to silver, and zinc 64 to zinc 66 ratio with nickel thin film electrodes. Double structure electrode results confirm the isotopic shift of helium-3 to helium-4 that may be ascribed to tritium production inside a plating vessel. Results seem to confirm the observations concerning the occurrence of low-energy nuclear reactions in solid that are, I mean, this is the dominant one for heat, but they differ from this one. And that's been an important thing to conclude. X-ray emission, isotopic shift, tritium production have been observed during electrochemical and electrochemically assisted gas loading experiments oriented to study LENR, and this is the work by George Miley. In the framework of this cooperation, experimental activity was carried out to look at this is a repeat of what I just said. Experiments have been mainly oriented to reduce contamination effects that are responsible for the strong criticism. Severe cleaning conditions have been maintained to increase the signal-to-noise ratio for X-ray measurements, for neutron activation analysis, and for secondary ion mass spectroscopy. Thin films, 250 to 400 angstroms in double spectral cathodes have been used for X-ray and transmutation experiments. 3 experimental runs, A, B, and C, with thin films have been carried out. The first run, A, was dedicated to the mass balance of the marker thing. So that was basically, I'll read it. Marker balance, zinc and silver with batch nuclear activation analysis measurements coupled with X-ray detection and tritium measurements. The second run, B, involved experiments in order to have the isotopic shift analysis and X-ray detection and tritium measurement. Third run, C, was carried out for further measurement of X-ray and isotopic shift. Since double structured cathodes, this is the Japanese person, errata-like experiments have been were conducted to test the isotopic shift occurring between helium-3 and helium-4. Okay. All right, so the thin film experiment, the experimental cells were realized by using only 2 materials, pure polyethylene and pure platinum, 99.98%, so they were careful about it. The cell was used with 15 cubic centimeter polyethylene vessel, so they were taking care of the materials. Thin films prepared by sputtering simultaneously over 2 target supports of pure polyethylene very close to each other in order to have a blank thin film electrode having the same deposition as the working one. So they were really paying attention to what they did. Anode was wrapped platinum wire. Cathode, cathode is a metallic thin film containing copper and or nickel or PD. The contact is realized with a C-shaped platinum wire inserted for polyethylene support. An analysis facility of the nuclear measurements laboratory of the Kennedy Research Center has been used for the experiments. So they did a radiation that they did by means of the Trigon 1 megawatt Mark II reactor, the neutron flux of 2.6 times 10 to the 12 per centimeter squared per second. Thermal to the mass ratio of 2 to 1 with a radiation time of 24 hours over 5 days and 10 minutes for long and short radiation respectively. Measurements have been done after a proper radioactive cooling time by using a coaxial germanium Ortec detector and an Ortec counting chain. Rough data had been obtained by Ortec Maestro 2 and on-the-ground softwares, pure standards and standard mixtures of zinc. Well, these are details. The high reproducibility of the specific activity of zinc and silver pure standards allow us to consider that the irradiation is properly optimized. That's the bottom line of that. X-ray measurements have been performed with a planar germanium vortex detector. So, in the first run, they call it copper 1A, has copper 450 angstrom cathode with a mass balance in batch mode. I'll get to the actual here's the definition of the batch mode. All right, black inventory, that's the raw sample, minus the blank inventory. So that's taking away, this gives some measure of the variance in the error. So they had what they had minus all the different isotopes and so forth that were here in the blank, and then in the cathode itself in the blank, and in the electrolyte in the blank. So that's a conservative estimate. And then in the not batch mode, it's just this minus that. So here we have the batch. So Cu1A refers to the batch mode. Nickel 1A is also the batch mode with a 1. Well, the copper nickel 1A is not the batch mode. Anyhow, they give a table that explains what went on. And then they have now, I think the thing to notice, if you look at this, is first of all, well, there's no evidence of weight reduction of the anode. That's the platinum. Above, that should be a 0.0001 gram in detected X-ray value. No correlation between current and inventory elements like zinc and silver has been found. Okay, so these things are uncoupled. And the other thing that I took away from this is these numbers are hard to see. But the percentage change in silver, very large. These are percentage changes. The percentage change in zinc, very large. These were for the various runs. Let's see, and the blanks, I'll tell you this. These zinc, you get a big zinc increase to one sample. A small increase of silver, that's showing they're uncorrelated.
There's no palladium, or was that last one, palladium?
This is electrolysis in palladium.
In palladium?
Yes. No, this might have been in nickel. No, this all refers to the electrons. Those are the things that are made. The copper palladium 1A is opposite. So there was some. So they were deliberately doing it not in palladium.
Those are the thin film cathodes. They're copper nickel.
Yeah, the thin films. That's exactly right. That's what they were announcing. That's what they're analyzing. So it's all in the thin film. It's all in it. You might know this stuff better than I do. I just asked Victoria to send me something. He sent it post deadline. That's what I was supposed to. Okay. Disregard this. And in this case, okay, it was damaged, but here everything is up. I mean, you get, and this is the error. This is okay. So this is the errata work, and this shows that the picture of it, there's detailed information about this that is readily accessible. But actually, Talbot is a real expert on this. There's an important paper done. Actually, when was that paper? That was done in September of last year. The one with the tritium and the Cougar. Was that September of last year? Well, there was an important paper where tritium earlier. It was a year ago. A year ago, September. The error. So this is the errata work, and this shows that the picture of it, there's detailed information about this that is readily accessible. But actually, Talbot is a real expert on this. There's an important paper done. Actually, when was that paper? That was done in September of last year. The one with the tritium and the Cougar. Was that September of last year? Well, there was an important paper where tritium earlier. It was a year ago September. And basically what they're trying to do is to reproduce their experiment.
Scott, I want to go back to your previous slide.
Yeah.
The basic issue is that tritium was made inside the black.
That's right.
The tritium diffused out.
That's right.
And in diffusing out, it decayed into helium-3. And the exponential decay of the line that's marked there is the remnant helium-3 that was found in the surrounding palladium of the cathode.
Yeah. So they really dramatically changed the ratio of helium-3 to helium-4 and reached this outside. But there was a gradient. They found tritium. Yeah, Ben.
The way Arata made that cathode was they flushed I'm sure they flushed the palladium blackout deuterium, get rid of the proton. Then they packed it in there and they electron beam welded the lid on that.
You got to speak a little louder.
They electron beam welded the lid on that double structure cathode. The electron beam welding is sufficient to give you tritium.
Is that interesting? Well, let me just finish, before we completely go into, sort of a free-for-all, let me just try to finish up here. All right. So they wanted to replicate the experiments of Professor Arata with particular attention to reproducing the measurements in the void phase of the double standard cathodes by Clark et al. That was the report I was referring to. Micromass, 5,400 noble gas mass spectrometers is allowing absolute resolution for helium-4 of approximately 1 times 10 to the 7th atoms, helium-3 of 2.5 times 10 to the 5th atoms, ambient air, helium-3 to helium-4 isotope ratio 1 roughly 4 times 10 to the 6. Parts per billion measurements of helium-4 require parts per trillion measurements of helium-3 if this is supposed to, if the latter is not significantly enhanced. Similarly, with a half-life over 12 years, the rate of production of helium-3 on experimental time scales is sufficiently small for modest amounts of tritium to require high sensitivity. So they have two cathodes. This is a misspelling, or rather this should be EAP2. We're prepared with following dimensions, and they're roughly the same, 60 millimeters long and so forth. It's a little longer, a little wider, and heavier. And they had a massive amount of palladium of 0.6, which is just with a larger volume, just like here. And they repeated current protocols that you see Arata's stuff is fairly well documented, and they could do what, something similar to what he did. This is the time, the 5 amps and so forth, particular amounts of time. And this just shows how they would get their gas out. They used a puncturing tip with the cathode.
Okay, this is independent data from the stuff that McCoubrey and Potter did. This is the replication.
This is the replication. Okay. And the punchline here is sample EAP2 yielded a potentially more interesting result this one. The initial sample, while only 1/4 of the volume of the EAP1, shows a higher concentration of helium-3, a lower concentration of helium-4. Helium isotope concentration composition of the sample is significantly different from the ambient air background, suggesting that at least some radiation was produced during the course of the experiment. Okay. So I get back to the conclusion. Control of contaminants ensured a satisfactory signal-to-noise ratio in the measurements. X-rays have been detected in the low